So this is where we left off last time. And now we're going to start off by discussing something called parallel coordinates. I actually need markers for this. And I did bring them. I'm just a little surprised that there aren't markers here already. Does anybody see any? No. Okay. I did bring some. Oh, look. Everybody knows scatter plots, right? So in a scatter plot, you have an x and a y axis, typically. X and y. Anybody know another name for a scatter plot? It's, well, in this case, it's also called a Cartesian coordinate plot. So imagine we have values along x and along y. Hopefully everybody remembers this from their school days. So we have a value of 4 and 3, for example. So to plot that on a Cartesian, in a Cartesian coordinate system, you would move over 4 units on the x-axis, 1, 2, 3, 4, and then up 3 units on the y-axis. Actually, I should draw it over here. And then we have our point. I think everybody knows that, right? However, what happens with a Cartesian plot if you want to add a third variant, like z, for example? Any ideas?
A 3D plot.
What's your name?
Casa.
Casa? Yes, good answer. You could extend it to 3D. That's one possibility. But then you have that shading and rotation challenge. But it's definitely a possibility, and you can do that for assignment 1. What if you want to add a 4th variant? Any ideas about a 4th variant?
Color.
Yes, what's your name?
Sam.
Sam, yes. Another Sam. So you could map that to color. This could be like the 3D. This could be color. What about another one? Beta, I'm running out of space. Could we do any more? It's another Sam. Yes.
Size.
Size, yes. You could use size. It's starting to get complicated, isn't it? These points in 3D space with different colors and different sizes. Could we keep going?
Can we have 2 separate plots? Like the graph?
Definitely, definitely. So you could then do like a scatter plot matrix. Now, the point is, wouldn't it be nice if there was a visual design or a coordinate space where we didn't have to do all those fancy things, and that was a little bit more scalable? Like, is it possible to think of another coordinate space where that supports more than 2 dimensions easily? So now imagine. This is all it is, really. Imagine taking this x-axis and rotating it by 90 degrees. So this is our x-axis. I'm going to draw a 0 in the middle. That's x. So I've just taken x and I've rotated it by 90 degrees. Y, I don't rotate at all. I keep it like this. And the two axes are parallel. So how do I draw 0.43, which is in Cartesian coordinates, in parallel coordinates? That's the big question. They are almost the same. So I go up 4 units on the x-axis, 1, 2, 3, 4. I draw a point. Then I go up 3 units on the y-axis, 1, 2, 3, and I draw another point, and then I connect the 2 points with an edge. So this point in Cartesian coordinates turns into 2 points and an edge in parallel coordinates. So these are called parallel coordinates. Did everybody follow that? It's not very complicated. Now the advantage of this is I can add another axis without too much difficulty. So this is x, this is y, and this is z. If I want to add another column, another data tuple, like for z, I just move up 1 unit and I connect the polyline to that data sample or that dimension of the data. And I can keep going. I can add another axis. I don't have to stop there. So this is alpha, and I can have a value, for example, of -2 on alpha. Here's my 0 point. It's not very well drawn. I move down 2 units, and I connect it up again, and I have now a 4-dimensional parallel coordinates plot. And I could add a 5th dimension, or a 6th dimension, or a 7th dimension, or an 8th dimension. As long as I have enough space on my screen, basically. Now, how much space do you have on your screen? That's a little bit arbitrary. A little bit arbitrary. It's somewhat objective. But I think it's safe to say you can comfortably fit up to something like 20 dimensions, 20 to 30 dimensions on a standard computer screen using this method. So it's a high-dimensional multivariate visualization strategy or design. Did everybody follow that? So the layout is n parallel axes, 1 axis per data attribute or dimension. And the axes have a minimum and maximum value from minimum to the maximum typically. And just like Cartesian, minimum to the maximum. So very simple conceptually, really. And we can add other things to these parallel coordinates like color. If we want to add color, we can add color. So this is an example of parallel coordinates with color. Right, so if a user selects an area here of lines, they can use color to help track where these lines go across the polyline plot. It does help. This is again a kind of cars data set. This is like very common academic high-dimensional data viz data set. So these are small cars, engine size, horsepower, and city miles per gallon, highway miles per gallon, weight of the car, and in length and so on. So you can see the different attributes here. This is from a tool that you may use in your assignment 1 called XMDV. So anybody can download XMDV and start using it. Is the attendance register been passed around? Did it make it across the aisle? Yeah? So this is what it looks like when we overplot. So just like in Cartesian coordinates, you can have too many data samples on your space and they overplot and they're hard to see. In some ways, it's arguably even worse with parallel coordinates because you have polylines rather than points, and polylines occupy more pixel space than points do. So this is kind of one of the limitations or challenges with the original parallel coordinates implementation. But we can use some strategies to alleviate that. For example, color, like we mentioned. So the polylines can be colored, but we can also use something called brushing. And brushing is simply a selection. So we take any axis, and then we select a range along that axis. So for example, all the polylines that pass through this area of the axis, this range of an axis. Those get a special color, and then we can see what they look like when they connect to the other dimensions. In this example, a narrow range of polylines along the pressure axis has been selected, and we can see that the pink, they're colored in this kind of pink, or I don't know if you'd call that pink, fuchsia or something like that. And you can see what happens to them when they connect to the other dimensions. So that's using a combination of colored polylines and brushing. Brushing just means subset selection. We can also, so this is an example with several dimensions. I don't want to count them all. I'm going to guess those are 20-ish dimensions, maybe more, maybe 25. But we can also group the lines into clusters and create a kind of hierarchical visualization. So we can cluster the large numbers of lines together. And that's what a possible implementation looks like. We can also replace the polylines, or we could add histograms to those polylines. Everybody here knows what a histogram is now. Well, you knew that before you entered this module. This bar represents the number of polylines that intersect this axis along this interval. So we can see, for example, the most polylines intersect the axis, the first axis here, because the histogram bin, or the histogram rectangle is the longest. So we can get an idea of the way that polylines are distributed across the axes. And if we want to add angular information, since all the polylines have an angle of intersection associated with the axes, we can also add that angular information to the histograms. So now this bar has an angle of intersection with the axis, and that angle is the average angle of all the polylines that intersect that axis. And it gives us an overview of what the data looks like before we start looking at the individual polylines. For very large data sets, and this is what it looks like when you have color. You can add color to those, and you can add curvature if you like as well. So this is what this looks like when you start interacting with the software. So this is using a data set size with 1 million records or high dimensional data tuples applied to the parallel coordinates plot with these enhancements added on top. So you can click on any histogram bar if you want and subdivide it in half, split it in half to get a higher resolution representation of the data in that area. And that's what's happening now. The user is clicking on different bins and then getting more details about the polylines that intersect those axes. And then what the user can do is then render the original polylines behind the histogram bars. Right, so this is the user adjusting the bin resolution. So the user can adjust the bin resolution of these histogram bins to make them more narrow or wider. That's really just a user option to make them some arbitrary level of detail. And this is what brushing looks like when it's done interactively on a parallel coordinates plot or with enhancements. So that's the user selecting a region. The user selected this region here, and then the original polylines are rendered, and the user then adjusted the opacity of those polylines. So right now the opacity is a little bit low, and the user can adjust the opacity of the original polylines and the histograms as well. So that's what parallel coordinates can look like when you start to interact with them and with enhancements like histograms and angular histograms and adjusting opacities and things like that. We're not going to go through the whole video because it is almost 10 minutes long, but you're welcome to have a look at that on the module YouTube channel. Any questions about parallel coordinates? So that was a very kind of quick introduction to parallel coordinates. Sam?
Can you also like map discrete data onto axes?
Good, Sam. You are like paying very good attention. I can see you'd have to be paying very close attention to ask such a question like that. The answer is yes. You can map discrete, non-continuous data. It's quite easy, actually. So imagine you just had data that was like country, for example. Like in assignment 1, you had country. You could just plot the countries. For example, one idea would be in alphabetical order along this axis. I'm not going to attempt to do that, but I'm just going to try it. So you could have like Germany, and all the polylines that correspond to Germany would start here. And then you might have a position for Japan here. And then the United States, here. So for discrete data, you just assign a position along the axis. Hopefully it's not a random position. Like it makes sense to have evenly spaced intervals in some logical order, not just random order. But yes, that's how you would handle discrete categorical data using this technique. Very good question. Any other questions about that? So I encourage you to use this for assignment 1. Because I think it will be could be very interesting. And you could handle a lot of data. So some people are asking me like, how can I make the data more interesting? Well, now you can plot, you know how to plot lots of diseases and compare them with one another. So one of these axes could be a disease, like different diseases. Like you could compare 20 different diseases on one axis. you could compare 20 different countries on an axis, or you could compare 20 different years on an axis too. So you have more options to play with. Like this can handle lots of different ideas. Okay, and we're not going to discuss this in length, but we'll just mention coordinated multiple views. So coordinated multiple views are the idea that we have multiple windows and each has a different view of the same data. And those views are synchronized in the way that they depict things and with their interaction. So in this example, we have data. This is flow visualization data. So fluid is coming in from the left, hitting this structure, and then carrying on to the right. So it's flow visualization data. That's the spatial view of the data. So we can see the flow in 3D space and how it behaves. But we can look at that same data with other views, as we know from assignment 1. Here's a parallel coordinates plot of the same data. So it's high dimensional data. Each property of the flow is mapped to an axis. Here's a spherical histogram of that data, same data. So all the vectors are normalized and then plotted from the center of a sphere, so we can see the frequency of those vectors in all directions. Here's a scatter plot view of the same data, and this happens to be like curvature of the streamlines versus the position of streamlines. Here is a histogram table, so every attribute, every dimension of the data plotted as a histogram stacked on top of one another. And when the user selects, for example, a certain range of data, like here, show me this. This is velocity in the negative direction, so going backstream, like against the flow, upstream, rather. The corresponding data in all of the windows gets updated. So it's all synchronized and linked together. So if we want to see upstream flow, the user can select upstream flow in one view, and then they get, okay, these are streamlines that show the upstream flow. This is what they look like in the histogram. This is what they look like on the scatter plot. And this is what they look like in the histogram table. And we'll just show one example of that. And these are interactive features, so it's hard to show them in just a slide. Really, we need to see, it's much more helpful to see video footage of such interaction. And this is an example, this is a real example from a CFD simulation, which we haven't talked about yet. So we haven't talked about CFD simulation data. But we know that Swansea is very active in marine turbine energy research. We know that's a very active topic here at Swansea University. Everybody's heard of these different projects. And this is related to those projects. So this is what coordinated multiple linked views looks like. Here we have a spatial view. Here we have a parallel coordinates view. Here's the histogram, and this is the spherical histogram. This is the standard histogram table. So the user has selected some data in the parallel coordinates plot, and then that same data is shown in the spatial view, the spherical histogram view, and the standard histogram view. So in this case, the engineers wanted to know, where does the flow go backwards or upstream? And that's that can be, it's a simple question conceptually, But with standard software tools, it's a difficult question to answer. It's very difficult to search manually for flow that flows in the wrong direction. But with these coordinated multiple views, it's very, very simple and fast, right? The user just chooses the negative x velocity in the histogram view, just brushes it, and boom, can see all the flow that goes in the wrong direction or the upstream direction. So I don't know if anybody can remember the first lecture, but when I was saying, like, everything is just a search, and visualization accelerates the search process. In this case, the search process went from infinite time, which was impossible, to a matter of just like 2 seconds. And that's only possible with certain visualization techniques. It would have been basically impossible for the engineers to just find out where the reverse flow is using their traditional tools. We won't look at that in its entirety because it's longer, but you're welcome to look at that in its entirety. Any questions on coordinated multiple views? Good. Good.